Hello everyone, I'm Ines Mustafa. I'm a PhD student in the Department of Electronic, Electric, Automatic and Engineering, University of Ribera y Virgili in Spain. It's my pleasure to introduce my work in the SP Micro Conference 2021. I'm going to talk about revealing the influence of annealing treatment on the performance of non-Fullerene organic photovoltaics. The outline of my work, small introduction about the organic photovoltaic and the procedures of my experiment, and some discussion about the results, then concluding these obtained results. Regarding to the introduction, which motivate for this work is the energy problem. As we know that the energy demand gonna be double 2050, and recent non-renewable energy sources during the consumption and extraction are causing environmental pollution. So one of the important solution is to use clean and renewable energy for the future, such as solar energy using sun, and one of the most important application using this solar energy in sun is the photovoltaic. Different generation was observed for photovoltaics. First, second, and third generation. In my work, I'm gonna focus on the recent third generation using polymer or organic photovoltaic. During the history of organic photovoltaic until now, recently it was like increasing step by step, but currently a sharp increase in the performance of this organic photovoltaic was obtained due to the addition of or the presence of non-Fullerene acceptors as a part of the blend with different type of donors, which cause improving the performance currently to 18.2%. Starting small introduction about the operation of the principle of organic solar cell, we can say that the active layer active blend, which is a light absorber layer, when the light incident, the exciton forms the exciton that separating the interfaces, and the interfacial layers support the extraction and the transfer of free electron and hole, and these layers are selected carefully regarding to their energy alignment. So in my work, we use non-Fullerene active acceptor, which is Y7, and donor PM6 as the polymer blend. And the structure of the organic photovoltaic is the inverted structure using zinc oxide as electron transporting layer and vanadium oxide as a hot transporting layer. So in the experimental part, the fabrication procedures is simply starting with the zinc oxide layer film fabrication by spin coating, then annealing. After the deposition of zinc oxide, we started we continued all the procedures in the glove box. Then the prepared solution has been deposited using a spin coating and annealed. Then the whole transporting layer vanadium oxide were thermally evaporated in thermal evaporator, also inside the glove box. And then a layer of silver were deposited over the vanadium oxide as a contact to form this shape of cell. And this vacuum holder used the cell to characterize all the electric and optical characteristics for the cell, as we will see in the next slide. So the main work was focused in this layer of active layer. So I made like a small scheme about the procedures done during the experiment, which is to study the effect of additives and annealing, thermal annealing treatments on the morphology and on the performance of the cell. We started with a Preston device, which is our reference, blend A, based on device A, without any thermal annealing and without any chloromethylene additive. This is used to compare with the effect of additives with using 2% of chloromethylene additive. And then to study the effect of thermal annealing, we use two different devices, C and D. Yes, thermal annealing and 0% of chloromethylene additive, and thermal annealing and 2% of chloromethylene additive. In this case, we can compare between the effect of thermal annealing between A and B and D, also between the effect of additives between A and B and C and D. Starting with the device performance using current density voltage characteristics, we can see that under light, the GV curve under light, it was noticeable that the 2% chloromethylene additives show higher current generated more than 0% chloromethylene additive. Also, it was interestingly that the JV curve under dark show lower leakage current for the devices with 2% chloromethylene additive. So these 2% chloromethylene additives improve the performance by superior enhancement in the GSC. Regarding the thermal annealing treatment, we will not see a large difference in the current, but we will see a main difference in the VOC value between the thermally annealed and non-annealed device like A and C and B and D devices, where the thermal annealing treatment improve the VOC of the device. So also the fill factor affected as the thermal annealing and the additives treatment, it was improving the fill factor and as well as the power conversion efficiency. That is why we can say that the combination between the thermal annealing and 2% chloromethylene treatments additives in device D shows the better performance parameters and the higher power conversion efficiency among the all other devices. So to explain this that obtained result, we make the further characteristics starting with the morphological characteristics using AFM. We can see that for 0% chloromethylene film, we can see that more aggregation and higher surface roughness obtained for these blends. However, we can see for the non-annealed devices from 0 to 2% chloromethylene additives, the roughness increased. However, the device performance improved. So we suggested that 2% chloromethylene additives has the dominant effect on the physical properties of the film by decreasing the effect of column interaction with the localization and decreasing the domain size, which leads to a sufficient and efficient separation of the excitons that provide higher current generated and better fill factor, which makes the effect of the morphology or the roughness obtained is less pronounced. And also, regarding to the thermal annealing devices, like it show a different network of fiber showing a smoother homogeneous surfaces, which reflects the better separation and more homogeneous mix between the BM6 and Y7, indicating like inhibition of molecular aggregation and more thermal stability, which is also known about the non-Fullerene acceptor. In this case, it explains the higher fill factor and GSC obtained for the thermal anneal devices, also with the additives of 2% chloromethylene additive. Another characteristic using electric and optical AQE, external quantum efficiency characteristics between devices, which confirm the higher current, also the higher integrated GSC for the 2% chloromethylene devices modified with 2% chloromethylene. And by calculations RPAC energy, it was interesting to see that the better lower value for RPAC energy was obtained for the device D, which has a superior performance. Also, it was interesting to see that these two slopes obtained for 0% chloromethylene devices, which also explains the drop in the absorption in the EQE more 800 nanometer here, which explains the more embedded traps that inhibit the current or the separation or make more defects that decrease the fill factor and decrease the GUC, as so in a table of the AGV curve. So further, UV visible spectra has been characterized for this using UV visible absorption. We can see that regarding the PM6 and Y7 for thermal annealing treatment for the device C and device D, thermal anneal device show higher absorption, while for device while for the 2% chloromethylene additives, we can see like a different effect. There is no shift for PM6, all have the same peak, only is the intensity. While for Y7, we can see like around 9 nanometer redshift. Also, a higher absorption peak intensity for 2% chloronaphthalene modified fat, which is mean that for the Y7 molecule become more tight aggregation, which typically is described by the regarding to the bye-bye interaction, and also the absorption from the Y7 acceptor efficiently converted into photocurrent. Then the major effect might be given from the non-Fullerene Y7 part that improves the JSC due to the effect of thermal annealing as well as the 2% of chloromethylene additive. So we can see that the overall evaluation of the binary blend from the UVB observes that 2% and thermal annealing treatment has a positive effect in the Y7 and BM6 like respectively. And the EQE spectra verify the paired review also here in device D4 to effect of 2% chloromethylene additive as we see here for the current. Then by describing the effect of the recombination with different light intensities, we saw like two different behavior for the devices at low light intensity less than 1 and at high light intensity more than 10 milliwatt per centimeter square, which is revealing to the, in case of the current, it reveals to the bimolecular recombination. Here we can say that for device, thermal anneal device and 2% chloromethylene treated device show more value close to 1, which is explain lower effect of bimolecular recombination, so it enhances the current. Also, this is confirms the 2% of chloromethylene additive and thermal annealing improve the morphology as we discussed before. Also, this is regarding to less recombination obtained in the devices. Regarding also to the ideality factor, we can see the same trend obtained regarding to the VOC versus the different light intensities, which is so lower or more close value to 1, which possess less trap assistance for the treated devices and more trap assistant recombination for the Preston devices. Furthermore, by characterizing the V effect versus the G photogenerated current, we can see this difference might be due to the resistance, where the treated devices has lower resistance than the non-treated one, the Preston one. In addition to the effect, the most important effect of the 2% chloromethylene additive, which show higher saturation current, which is also confirming the higher current generated in this case. Another characteristic using the impedance spectroscopy for the fabricated devices, where the V built-in value was higher for the treated more than the Preston, which indicate also or confirming the higher value of the VOC for the treated more than the Preston one, as well as it explain the effect the effect of trap as we discussed before. So it has a lower effect of trap or disorder, which gave higher value of V built-in and better value for fill factor, and as well as explaining the better performance obtained for the devices. Also, we can see in device D, in this case, that in device D demonstrate like a superior high chemical capacitance among the other devices due to the effect of tuning the 2% chloromethylene additives with thermal annealing, resulting in less localized state in the band gap that leads to better VOC and fill factor, as well as the power conversion efficiency, as we see in the characteristics. Another important characteristic using density of state as a function of energy, which also confirms the EQE characteristics with RPAC energy, that the 2% chloromethylene additive has lower trap states than the 0% chloromethylene devices. Finally, using Nyquist plot, we can see that from these additives we get less resistance, less arc size, and less like accumulation of the current, resulting in less resistance, as we see here also from Nyquist and from the plot. This is also confirmed by the resistance obtained from the JV characteristic curve, and this data has been fitted using the Bay model as shown in this circuit, confirming the same value of resistance. And all the data was in a combined or in a good alignment with showing device D is a champion device that combined between two effects. So as a conclusion, we can say that both effective thermal additives and thermal annealing and 2% chlorinaphthane additives show better performance or parameter for all devices. However, this in the case of the binary devices. In this paper, it has been recently published in Solar RRL, and it discussed all the details about this work along with the effect of this treatment in the ternary like a ternary system also, using another non-Fullerene Fullerene acceptor besides the Fullerene acceptor to see the effect and the strategy of the optimization for binary and ternary device. I would like to acknowledge my funding agency. Also, I would like to thank my Professor Louise and Professor Paris, and thank you all for your listening. And for sure, your questions are more than welcome. Thank you so much.